Alright, in this video we're going to continue in this adaptive control realm, but move more towards a parameter estimation. And so last week, and I think the week before, we talked about MRAC controllers, which is a model reference adaptive controller. And basically the way it works is you take your reference signal and you take your error signal, and this goes through your controller like normal, and this is your control input, and this is your plant, and this is Y, and this is fed back through your sensor block, and this is just a standard controller, okay? The adaptive part is that you take your reference command and you also feed it through a reference model. And this creates a Y model, and you generate a Y tilde signal. This Y tilde signal, what you do with this is you run it through your adaptation law. And what that does is it creates an update. Technically, this isn't an input, it's a parameter update, so it goes through the block. And so this adaptive element runs through your controller and updates the parameters in your controller. So if you have a feedback linearization and controller in there where you're trying to, like an inverse dynamic controller, where you're trying to cancel out the dynamics and make it linear, that assumes you know what your parameters are. And so this controller sort of tries to update those parameters. And so it's a model reference controller because you're trying to match a model, right? You want Y tilde to go to 0, and you also want your parameter estimates minus your actual estimates, which are A tilde, to go to 0. So you want both of those to go to 0. Not to mention you also want your error to go to 0, right? You want E to go to 0. You want all these things to go to 0. So it's a model reference controller because you're trying to get your Y to match your Y model. But then at the same time, you also have an adaptive controller because you're trying to get your estimates of your parameters to go to 0. And so this is a model reference adaptive controller. Now, this whole model here, sometimes you might not want to do that. Maybe you want an estimator. So the nice thing about this controller is that you also estimate your parameters here, right? So you sort of get an estimator on board already, but you have to do all of this like model reference stuff. And say maybe you don't want to do that because you do have to add this computation that creates extra complexity. So what might be nicer is that you take, let me get a different marker here. Go ahead and throw this one out. What might be nice is if you just take your reference signal and your error signal and your controller and U and G, and you go ahead and take Y and H. You have the standard block, but instead of having the reference in there, you do what's called a self-tuning controller. And so instead of having a model run through here and run that through the estimator, you take your control input and you run this through an estimator. I'm going to call this, what do they call this in the book? They just call it estimator. I need to pick a letter then here, don't I? I'm going to call it F for filter. And you may even take the error signal and then run that and update your controller. This here is called a self-tuning controller. And so you have MRAC, MRAC versus ST for self-tuning. Now you might be wondering what the benefit of this is. Well, the benefit is that you don't actually need to measure. Here's your error signal. So if you don't use this, right? Say you just use your input U. You actually don't need to measure the output. You don't have to have this GM here. All you need to do is measure, say, your error signal, right? Which is just coming from your reference, which you have because it's part of your computer, and your sensor block, and then your control input, but you don't need this model up top. Okay, so it gets rid of one little piece of complexity. And the downside is that the derivation is completely different. So the upside is you have this estimator that just kind of runs on the side, and you don't need to necessarily include it in your dynamics. Because if you remember from the MRAC controller, we had a
we had like a dynamic update for our parameters. Maybe you don't want to do that. Maybe you don't want to necessarily guarantee stability or something like that. Well, of course you want to guarantee stability, but you don't want to incorporate it into your dynamics. Because we had m hat dot. Remember, we had m hat dot in there, and that equaled, negative gamma vs or whatever. And this dynamics, you have to include that into your model. And maybe you don't want to do that. Maybe you just want to have something that just is like a least squares estimator. Okay? And so instead of integrating that parameter on the fly, which may be prone to integration errors, you just want some sort of estimator. And again, that's where the self-tuning controller comes in. Okay, I'm going to make this a two-part series. We're going to do an example problem after this and show you how to do this will probably be a three-part series, but I'll probably wait till next week to do another one. So we're basically going to take the last problem that we just did, the mx double dot equals u, and we're going to derive a self-tuning controller instead of a model reference adaptive controller. So that'll be in the second video here coming up.